Hi, everyone. I'm Ibrahim Sabek. I'm an assistant professor in the CS department at the University of Southern California. I'm mainly working on large-scale database systems, so I'm more on the applied side, like very, very much. And today, I'm very excited to share with you our recent work on how we use the hybrid classical quantum solvers from D-Wave here in improving a very crucial operation in database systems, which is the query optimization. OK, so before we start like the details, how many of you heard about database systems before, or the term of database management systems? OK, great, like few of you. Databases are key for everything. And if you have applications with large-scale data, that using database is the right choice for you, because this will hide all the complexities that you're going to face when you're dealing with this data. And applications with large-scale data are around us everywhere, in many sectors, in many domains, like, for example, health sector, retail management, social media, education, and many others that we are dealing with on a daily basis. OK, so usually we are having database management systems. We refer to it as a DBMS, like to deal with everything or aspects related to the data, like querying, storing, processing, and everything related to that. So DBMSs are very complicated software and they have many components to handle different aspects of the data. Today, we are not going to touch on all of them. We're going to mainly focus on one component that deals with planning how we efficiently execute the user queries. So that's basically the objective that we have. So first of all, what are the database queries? What are examples of the queries that we are getting from the users and we want to try to answer efficiently? So I'm going to give you an example to better answer this question. So assume that we have like an application that includes the data of the students, the HR, professors' data from different departments in a school. And these tables show some kind of sample of the data that we have in these tables. For example, here, we have in the student table, we have 2 columns, name and department. And for each one of these tables, we have samples of rows. We call them sometimes tuples. And you see an example of Sam, Mary, and so on. So this row represents the data point for a specific entity or a person. And assume that we have a simple query like that. We have some users, issuing this Q1 and Q2 queries. These are very simple queries. For example, the first one is trying to find for each student the HR email of the department that this student belongs to. And the second query is the same thing, but now for the professor, trying to find also for each professor the HR email of the department belongs to. And what we are looking for in the DBMS is to come up with an output like this. So you pass the queries to the DBMS engine, and then you get an output in a relational way like that. So if you look at the first query, we get a simple table, getting some information from 2 tables, like student and HR. And the second one also following the same pattern, which is getting the data from professor and HR. So the question here, how do we get this? How do we get these tables, at the end, the output here? So the DBMS will simply try to join relevant tables included in your question or your query to get the results that you're looking for. We call this join queries. So basically, in the first query here, Q1, we are trying to get the results that we have here by joining 2 tables, student and HR. And how can we do this? By finding the matching tuples from the 2 tables based on a join column. Like, for example, here we have between a student and HR a department column, which is the joint one. We call this a joint predicate or a joint condition. OK? So that's a simple query of a join. How do we actually plan to run this inside the database management system? Now, let's get somehow a little bit deeper inside what's happening. So let's focus on query 1, which is trying to find the HR email of the departments for each student. And first of all, users try to write their queries in a more declarative way for the DBMS engine to understand. This is an example of a something we call SQL syntax. And you can see here in the syntax, we are mentioning the tables that you are trying to join, like student and HR, and the condition based on the department in these two tables and so on. After that, we pass this query to the DBMS engine. It parses it, and then it forwards this to the query optimizer, which comes with a plan like this. So this is the execution plan that they are looking for to run. And basically, you can think of it as a DAG, a directed acyclic graph of sequence of operations. And in this specific example, you can see first we have like two sequential scan operations on the two tables, HR on the left side, student on the right side. And then after that, we are running a hash join algorithm. This is like a join operation implementation, building a hash table data structure based on the left side and probing it with the right side. And then after that, they collect the results in the final step and then extract only the columns that we are looking for, which is name and email. These are basically the sequence of steps that we have for this join operation. But as you can imagine, you can ask yourself, what's the problem here? This is like a very simple thing, right? It's simple, of course, because we don't have so many input relations that we are trying to join. Only we have two input relations. So what are the different options that we have to join these two input relations? It might be two maximum, because here the order makes a difference. If we have the HR table on the left side and the student on the right side, or the student on the left side and the HR on the right side, because we have other step after that, which is the hash join algorithm to build the hash table on one relation and then probe it with another relation. So maximum in our case here, we have two alternatives planned, right? That's the thing. So that's easy. But real-world query workloads are more complicated than this. So let's have a more complicated query example from a typical workload that everyone knows in the industry of the database, which is called TBCH workload. This is basically a workload used for benchmarking or like evaluating the performance of decision support systems. And you can see here in this query, this is like the semantic of the query. We try to find the revenue for suppliers in a given region over a time period. So we have multiple dimensions here. We have multiple tables to join and get the matching results from them. And this is the SQL syntax corresponding to that. And you can see here, compared to the previous example, it's more complicated. So here we have 5 relations to join, and we have more join predicates to find the matching tuples based on. Now, if we want to build a plan for that, it will be something like this. It will be more complicated. Now, we have 5 relations to join, and what we are doing here is that we first pick the first pair of relations, we join them, and then we pick another relation to join with the result of this first join, and so on. So there is a specific order that we have to mention to the DBMS or to figure out to execute this plan. And since we have 5 relations, we might have many, many alternatives here. In fact, if you have n relations, theoretically, you can have up to catalan of n minus 1 times n factorial of the combinations of this relation, which is a very huge space. So in this case of the 5 relations, we might end up with 1,600, and even more alternatives to choose from. And for example, 18 relations, we might end up with more than 10 to the power 23 alternatives. We're going to see an example at the end in the live demo running a query of 18 relations to show you how is it hard. So you can see here that this is not an easy problem to solve. However, we already have solutions for this in the classical database management systems, but all of them are based on heuristics. So basically, we combine all the wisdom that we got from all the engineers in the database and try to find some rules to filter this alternative somehow and come up with the most efficient from our perspective. Okay? But of course, this is a classical computer, and we are not going to explore all the alternatives that we have in the search space. So we have a very high probability to miss very efficient plans that are not encoded in the heuristics. And we tried to solve this problem somehow in the classical by going to investigate different solutions like the machine learning, try to predict a plan somehow. But still, we are capped with the classical capabilities that we have. So we're not cover as many as we can in the search space. OK, so here, since we have very different alternatives, complicated join queries require join order optimization solution. So the question that we are trying to solve here, can we think out of the box, try to, explore the quantum computing capabilities that we have to, like, for example, using the hybrid classical quantum solver that we have, specifically the CQM, as we're going to see, to try to cover more alternatives in the join order and come up with an optimal solution from our perspective that's better than what we have in the classical domain. And the one caveat here that we have to emphasize on is that how can we do this in the query execution runtime? Because this is an online setup. And databases use as post queries. They try to buy something or try to do a transaction over a bank account or something like that. This has to be in a real time. So whatever you do, it has to be minimal overhead. So can we do that? And as you can guess, since I'm standing here, the answer should be yes. That's the case. So I'm going to show you that it's even possible now with the current solution that we have from the solvers to have a practical solution with them. OK, so we specifically choose the classical quantum hybrid solvers because they are somehow matching the specs of the problem that we are trying to solve. Basically, they are successful in mapping very large problem space to the QUBO. Of course, it's iterative and also combining some classical heuristics, but this is fine in our case because we are still also having some heuristics on our side to encode that can help in navigating the search space. So we combine the benefits of both worlds in this case. And with the QPU, we can find more solutions that we can't reach out to if we have like the classical part only, and then we can heuristically refine these solutions after we get them from the QPU. So that's basically a perfect fit for our case. We started our initial implementation of this solution for the query optimization using the CQM, and we choose this specifically because of the powerful representation of the constraints that they are providing. You can represent the equality and the inequality constraints explicitly in your code. And also, it's very easy to program with. You don't need to go for a low-level programming style to do this stuff. So it's kind of a perfect fit for us as a system developer to explore with it. So we take the CQM as a baseline for evaluating the performance of these hybrid solvers to see how practical they are. So this is like a workflow for our architecture of how we use that hybrid solver or the quantum computing capabilities and integrate it with a real database management system. So our real database management system is right next to the shaded box here, which is called the execution engine. We picked one of the widely used open source database management system, which is Postgres. What we do exactly here, we get the user queries on the left side, and then we pass it to our constructor for the join order optimization, which is basically using constrained QUBO representation that will be passed to the CQM and also having all the encoded constraints and everything. Once we do that, we pass it to the quantum annealer. We get a specific join order recommended from them at the end of the iterative process. And then we use this as a hint. We send it at the real time to the classical query optimizer. So we are still dealing with a query optimizer, but giving it a hint from the quantum space. And then we get a complete plan, like what I showed to you, and then we run it, get the results, and send it back to the user. It's a very simple thing, but it's very powerful. And we already published this initial results in a SegMod workshop, which SegMod is the biggest conference that we have in the database community. OK, so giving you some details about the simplicity that we experienced when we dealt with the CQM in implementing our stuff. I'm not going to go through the details of the QUBO representation, but I just wanted to highlight here how is it easy for us to represent the problem with few lines of code. So basically, we have three main constraints that we have to encode in our join order problem. First one is to encode the shape of that tree that I showed to you. So basically, in each step that we have, let's say step J, if this step is including a set of relations, we want to make sure that the number of relations in this step is J plus 1. For example, in the first step, we have two relations to join. In the second step, it will be the output of the join of the first two that we have, and a new one. So in the second step, we're going to have the output of 3 relations. The fourth step will be the output of fifth relation, like 5 relations and so on. So we keep adding the number of relations by 1 over the steps that we have. So how can we represent this? As you see here, this is like simple for loop here. Another constraint that we have is enforcing that the solution that we have is consistent. If I pick 2 relations in a specific step, I want to make sure that other relations that are joined with them after that still working with this pair that I had. So it's like incremental increase of the operands here. And we also use equality constraints simply, as you can see here, to add. The last constraint that we have here is to make sure that the join predicate that you are applying on the 2 relations currently that you want to join, they are coming from these 2 relations, not predicates applied to other relations. And you can also use inequality constraints like what we have here to represent it. So you can imagine here that the code is not that big, but the potential performance, again, that we get out of this will be huge. So giving you some kind of experimental evaluation evidence about this. So what we did here, we compared our approach, which is in red bars here, with a recent baseline that tried to use quantum-inspired digital annealer. This is not a quantum annealer, but it's a quantum-inspired digital annealer, using some kind of QUBO representation as well. So it's a perfect fit for us to compare against, and also using some kind of similar encoded constraints like what we did. And we used the job workload. This is the join order benchmark, a standard workload that we have for evaluating the complicated join queries. And on the x-axis here, you can see the different queries that we are using. These are the IDs of the queries. On the y-axis, we have the cost that we get after choosing the join order with whatever baseline that we have, with our hours order. And as you can see, the higher we go, the more overhead that you get, because this is higher cost. In all of the queries, almost we get the lower cost. This is just an estimation for the cost, not the real-time execution. I'm going to show you at the end a real demo here. Now, using the same job workload that we have here, how this reduction in the cost will be reflected on the running time as well. So you can see here that the performance gain varied between 1% to 98%. So you can actually have reduction of the performance gain to the half that we have here over the other costs. So the second experiment here that we have, we replicated the same setup, but we used a different workload, which is more complicated in terms of the number of relations. As you can see here on the x-axis, we are changing the number of relations. We started with 18, and then we finished with 50. So this means that we have 50 relations to join. And you can imagine here, I mentioned in 18 relations, we have more than 10 to the power 23. You can imagine here with 50, it will be way, way more than this. And as you can see, we still have better performance gain. And this is consistent with what we had in the job workload before. OK? So now, since I finished this experimental thing, let's move to the fun part, which is the demo that we are going to present here. So I'm going to show you here, this is a real demo of our system compared to the Postgres, the default Postgres. So here in this demo, we prepared a list of different workloads, complicated workloads in the database community. As you can see, I'm going to select job workload. This is the same one that we used in our experimental evaluation. So I'm going to select it here, and then pick one of the queries in this workload. So I'm going to select this Q1. As you can see, this is the SQL statement. This is a very complicated query. Here we are trying to see, to join 18 relations. And basically, this query is trying to find the voice actresses, the female voice actresses that are involved in some kind of US-produced movies. and in a specific period between, like, I think 2000 and 2010, and having specific, pattern in their name, like, starting with AN, or like having AN in their name. So this is like very, very, constrained one. And as you can see, on the left side, we have the quantum augmented approach. And the right side here, we have the default Postgres system. So now we issued the queries while I'm talking. We get the results from both. Now you can see the breakdown of the results here. So first of all, to make sure that the results are correct, both of these results are the same. So they are getting the same results. So we don't have any heuristics in the results. We get the exact results from both. Now the difference will be in the execution time. So here on the left side, we have the QUBO overhead. This is like the time that we have for accessing the QPU and solving our optimization problem there. This is like around 32 milliseconds. After we get the hint, we pass it to the classical query optimizer to start completing the plan. The planning time will be almost 2 seconds, which is very comparable to the time that we have also in the classical database system, so we don't have so much overhead. Now, the interesting part will be the execution time. This is the execution time after picking the join order plan and then running it. If this plan is very efficient, then you're going to see much more efficient execution time. And as you can see here, the execution time for the plan that picked up by the quantum here is almost 2 seconds, less than 2 seconds. But here with the classical one is like 15 seconds. So this means that we didn't achieve even like very close plan to the optimal solution in the classical part. And with the quantum part, we had more efficiency here. We wanted to get more insights about this. We actually visualized the query plans coming from POS systems. And as you can see here, this is like the first one here is coming from the quantum augmented thing. This is the tree that we got, as I mentioned before. But the most interesting part here is the representation of the operations that we have in this plan. So the most interesting part here that the most time-consuming relations that we are trying to join are picked up like with parallel operations by the quantum, which is something that we didn't figure out with the classical approach like we see here. They only focus on sequential scan, so they didn't get to the parallel part. Why is this? Because in the heuristics, if we have the threshold of the, we have a threshold, like if your relation is less than this threshold, you don't need to go for the parallel. But here in this case, they tried different combinations in the join order, and based on the cost estimate, they figure out a plan that's beyond the heuristics that we have. And once they run this, we get better results. Okay? So now I finished the demo, so I'm going to show you one more slide here to conclude what I have. So basically, what we did, we just scratched the surface. We didn't explore the full potential of the quantum computing in a real-time setup. We just focus on the CQM, but we have more hybrid solvers to investigate. Basically, NL solver is very promising. Actually, we started to play with it, and we got even better results than here, but I didn't include it in this demo because the results are still very, very early, need more investigation about this. Hopefully, we'll present it like in the next conference. And also, we can actually have more database tasks that we can solve with this. We just focus on the query optimization of one query. We can have multiple query optimization. Like if you have different queries coming at the same time, how can we optimize them? And also, other optimization problems in the database stack, like knob tuning, how you change the configuration of your database components. These are also very hard problems that we have now. Data partitioning layout, how you partition your data in a way that could be dynamic based on the user queries. Now we try to customize this layout for each user, which is like a very crucial problem. Also transaction scheduling, query scheduling as well, not the transaction only. So we have many, many other optimization problems that we try to investigate also with this. And since we got some kind of initial promising results in the real-time setup with the query optimization, we're very optimistic about this also in the other problems. So I just wanted to conclude with one statement here. Yeah. Basically, we can use the quantum computing in an online setup in a very crucial application like the database applications. And we have Still a long way to improve this, but we just started this, and I think it's promising. And thank you so much for your attention. I'm going to be available here if you want to discuss anything. After that, happy to take any questions, whether online or offline. Thank you.